So this lecture is going to focus on solving limit problems and continuity problems. And what I want to do is, before we begin, summarize the key ideas, the key tools that you have to solve these problems. And the first thing I want to point out again is when you describe the limit as x goes to a, what you really are saying is that you include the left side and the right side limits in that. So this is just, again, a shorthand notation for saying the limit from the left equals the limit from the right. The second is the tools that we have to actually evaluate the limit. As I said, these are just tools in your toolbox. A function is point continuous if you can just evaluate the limit by plugging into the function. Of course, this means that the function has to be defined at that point, the function is continuous, and so forth. The second tool you have is the extension theorem. So essentially, you extend the rule defining the function in a continuous manner, and that's how you evaluate the limit. And again, these are fairly straightforward tools to use if you just follow the standard procedure. So let's take a look at some problems. And the problems get progressively more sophisticated as we go forward. So let's just start here. So I'm saying let's look at the limit as x goes to 2 of this function. How do you interpret this, and where do we go from here? Okay. Again, I'll work the first problem out, and as we go, you should jump in and try to work these out more on your own. So the first thing is I always want to look at the function, right? Again, think about what the function is. Whether you write it down or not, take a moment to think about it. I've just given you a shorthand notation. What the function actually is, the function rule is 4x squared plus 3. The set x is real numbers. This is defined everywhere, and all the values are contained within the real numbers. So, okay, no big deal, but we should be thinking about that. Are there any simplifications we need to the rule? Not in this case, right? Okay, now we're going to just follow a standard algorithm, a standard procedure. So again, you don't need to do mine, but you should develop a standard way of solving problems. Each problem should not be different. They should all fit according to your algorithm. So the first thing we're going to do is note that this function rule is a polynomial, right? So if I look at this, what I have is a polynomial. A polynomial, for example, second order polynomial would be a constant times x squared plus a constant times x plus a constant. If it fits in this template, it is a polynomial. It's as straightforward as that. Okay, so in particular, I can identify the constant, so we have a polynomial. Okay, so let's just go forward. Is the limit point an element of the domain of f? So what is the limit point? The limit point here is 2. And yes, 2 then is an element of the domain of f. So we check that box. Next, is the function point continuous at a equals 2? Do we know if it's point continuous at a equals 2? Well, it's a polynomial. So polynomials are point continuous, and so we can evaluate them just simply by plugging in, right? I mean, again, it's just a fixed process. So how are we going to evaluate the limit? We're going to use point continuity, right? So we have the limit, right? I'm just using, this is the limit, identifying the function. I'm just plugging in using the definition. Now we'll just evaluate the function and we're done. So everything just falls into this format. I don't really need the details of the function get worked out really on the side. It's everything is going to have this same general template. You don't have to do it, but it's there. Okay, and so that's the answer. I mean, when you can plug in, you just plug in. All right, now here's an example. You guys pause it, jump in, do it. Let's see how it goes, okay? I'll wait a moment. I mean, pause it and go ahead. Okay, I'm going to jump in and look at the same thing, okay? So again, take a moment to think about what you're doing. I mean, there's my rule, okay? This is the function rule. That's what's given. Again, it's a shorthand notation, right? They're saying that I'm giving you the function rule here. There is a function here. What's the domain here, right? The range will be in the real numbers. What's the domain here? Well, what am I going to do? It's always the same rules, right? You see, you're always using the same tools over and over again. These tools are algebraic. But I have a over b is undefined, provided b is 0, right? If the denominator is 0. Well, what's the denominator here, right? The denominator is 2x plus 1. So when is 2x plus 1 0? Well, when x is 1/2. I mean, again, I'm not suggesting you have to write all this. I'm not suggesting that at all, but I am suggesting you should understand that there's a mathematical process behind everything you're going to do. This is not, again, my opinion, your opinion, somebody told you. Everything we're going to do is a mathematical process. So in particular, I know that x can't equal minus 1/2, which isn't the issue, right? I'm talking about for my limit point too. So let's just go through here. The second thing I want to notice at this preliminary step is this function is a rational function, right? It's a polynomial divided by a polynomial, and 3 is a polynomial, right? It's a 0th order polynomial. It's just a constant. So it does fit the polynomial template. Okay, let's go through it. Is the limit point in the domain? Notice we cover all the cases. The limit point in an element, this symbol means is an element of this set. Well, the limit point is 2, a equals 2, right? And that is in the domain. So check, the function is defined there. Is the function point continuous at a equals 2? Yes, it's a rational function, so it's point continuous, so we know how to evaluate the limit. So we're going to evaluate the limit using point continuity. So again, we're going to follow exactly the same steps as we did before. I just like working it this way with the abstract version because they're all the same. I just plug in and I evaluate the actual value on the side, and you're done. Again, there's no stress, there's no magic. It's just a mechanical process. We're not thinking or trying to understand it or interpret this. It's just a process. Okay, here's another one. Let's just again go through it and see what's going to happen here. First thing is I want to look at the function. Again, look at the function. I mean, you can try this and see what happens. Again, pause it and see, and then come back and compare. Okay, let's see. So again, it's always good to think about this stuff. So what's the domain here? Again, I have a over b. A over b is undefined when b is 0. So x cannot equal minus 3, right? So x cannot equal minus 3. Which is interesting because, of course, we're trying to get to minus 3, so we'll cross that when we get there. Now, it's usually a good idea to see if you can simplify the rule. For example, this form, again, it's not good or bad. This form is useful, I'm not going to say essential, but it's useful for determining things like the domain. So this is useful for determining the domain. But it's a rather clumsy rule, and if you can simplify it, you should try to simplify it. So notice, as long as you're not talking about x equals minus 3, right? Because if you're talking about x equals minus 3, it's not defined. If so, for x not equal to minus 3, algebraically, I can factor the top. And again, things don't cancel. Be careful about canceling things, as I mentioned before. People make a lot of mistakes by very sloppy cancellations. Things don't really cancel. They turn to, well, it's 1. 1 times the quantity is the quantity, right? And that's really how it cancels. So take your time on that so you don't make a mistake there. That's a big problem. So again, these rules are algebraically exactly the same, right? The benefit of the original rule was it tells us the domain, right? Because they didn't tell us the domain for this problem. But our algebraic manipulation made the rule simpler. This is the step where, again, people have trouble. And again, some of the problems in the book involve very specialized gimmicks. You should understand that. Very specialized gimmicks. They're not general problems at all. They're very specialized gimmicks and tricks. But again, this is typical. I simply simplify it, again, in the obvious way, right? If there's an x plus 3 in the bottom, I look for an x plus 3 in the top. I'm not randomly looking for things. I'm looking for something to cancel this. So this is a much easier rule. Okay, and let's go with it. Okay, so again, these are algebraically equivalent as long as x is not equal to minus 3. So again, let's follow the process. Is the limit point an element of the domain set? A equals minus 3. No. So we can't just plug in. We can't just use that one wrench, right? We have two wrenches. We can't use the one. We'll use the other, the evaluation theorem, right? So is the function point continuous? It can't be, right? If it's not defined at a equals minus 3, it certainly is not going to be point continuous there, right? Because you have to be defined. All right, so again, here's the definition of point continuity, right? I just can't plug in minus 3. This function is simply not defined there. So we don't have, again, you don't have to waste time thinking of it. You only have one other wrench that you can use here, right? You don't have, you either plug in or you use the extension theorem, right? I mean, again, it doesn't take a long process. Don't waste time needlessly, I don't know, thinking about what happened in nuclear physics class today. It doesn't make any difference. So if I'm going to use extension theorem, I need an extension. I wonder what that might be. I mean, look at the function on the screen here. What could it be? I'm thinking I need a rule that could also be defined at x equals minus 3. I need to extend this domain, the rule to cover this point. Clearly, the original rule they gave us is not defined. But this rule is algebraically equivalent to this rule, and this rule works everywhere. All right? So that's my extension. Notice the rule is exactly the same, right? The rule is the same, but these are different functions because I've extended the domain. I've extended the application of this rule to include x equals minus 3. So it's an extension, right? And it's usually that straightforward. Again, don't make a mountain out of a molehill. The cases in the book that aren't this straightforward, they're specialized gimmicks. There are certain types of problems that have specialized gimmicks that only apply to those types of problems. I'm not a fan. I'm not putting it on the test because, again, what's the point in memorizing this? If I was interested in memorizing it, I would just write down the list of possibilities and that's it. But again, if you do the homework and you see these things, be sophisticated enough, savvy enough to know that you just have to look it up, right? I mean, other people may ask you to do it. What are you going to do? Just look it up. Okay, so let's apply the extension theorem, right? Notice, before I jump in there, this function here is in fact a polynomial, right? It's a first order polynomial that fits the template. If I can put it in a template, then I can say it's the polynomial. Okay, and polynomials are point continuous, so I'm in pretty good shape. So let's go. So my extension is here. Check my conditions to use the extension theorem. Again, why are you going to have problems? Because you don't satisfy the conditions, I'm guessing. Notice the two rules are equal. The rules that define the functions are both equal as long as x is not equal to 3. My extension is a polynomial, and so it's point continuous. And so, I mean, I'm good. I can apply the extension theorem, right? And again, it's going to look almost exactly the same. I follow the same template. I'm going to just, I don't know, I'm going to replace it, the specific rule with the name f of x. Now I know by the extension theorem that they have the same limits, right? And because g is continuous, I can just plug in, use the definition of point continuity for g. And they'll always work like this. That's the beauty of it. Once you come up with the extension, and again, there are some gimmicky problems, but you know, those are the ones you suffer for and you think, oh, this is so crazy. Look for it, but most of them, they'll just cancel out and it'll work like this. And so I evaluate that, what is g of minus 3, and you're done. I mean, it's It doesn't have to be a painful process. It's pretty straightforward. You have these two wrenches and they're pretty good. So why don't you guys try this one? Pause the video and give this a shot and see how it goes. Again, these are all test type questions. You should be comfortable with this without stressing out. Okay, let me jump in now. What do we have? Let's define the function and again do the work that needs to be done. So you need to know the domain because you need to know if the function is defined there. Again, a over b is undefined when b is 0, so x cannot be 0. Again, I'm not suggesting writing all this out. I'm suggesting this should run through your mind. So I know x is not equal to 0. All right. So let's see, can we simplify our rule any? I mean, let's see if we can simplify the rule. Again, it's purely algebra. It's not calculus. It's purely an algebraic step. I have, as long as x is not equal to 0, because clearly this rule is not defined at 0, but as long as I'm not 0, I want to get rid of this x squared in the bottom. So I'm going to try to factor it out of the top, and it does. And again, it cancels because, well, it doesn't really cancel. It equals 1. X squared over x squared equals 1. And 1 times a quantity is that quantity. So these two rules are algebraically equivalent as long as x does not equal 0. And that's our scenario, right? They're the same. So let's go through the process. Is the limit point an element of the domain? Yes, the limit, no, I'm sorry, no. A equals 0. The limit point is 0. Right? The limit point is 0, and it's not in the domain. So we cannot just, is it F point continuous there? No, you can't. You can't just plug in there. Right? So I can't use the definition of point continuity. So so if I can't use option A, I use option B. I use the extension theorem. I don't have another choice. So let's go to the extension theorem, and we have to figure out an extension. So here's my function. I wonder what that extension could possibly be. See if you can write it down. All right, it's going to be, I'm going to take the simplified rule. Right, so the rule is exactly the same in the extension as the original function. And again, the key is it's an extension because I extend that rule to include x equals 0. Okay, so this is how you look for the extension. Again, if it didn't come out naturally, we wouldn't use it. There'd be a different tool or a different technique or something else. The fact that we use it is because, well, it's convenient. Okay, this function is a second order polynomial, right? X squared minus 5 is a second order polynomial. Notice I can put it in this template, a constant x squared plus a constant x plus another constant. Notice the middle constant is in fact 0, which is valid. So again, if I can fit my rule into the template that defines a polynomial, it is a polynomial. If I can, it's not. But if I can, it is a polynomial. And polynomials are point continuous for any value of a. Okay, so I'm all set up. So I know that the rules are the same as long as x is not equal to 0, right? Because at x equals 0, our function isn't even defined. But outside of that, x value, they're exactly the same. My extension is a polynomial, so it's point continuous, and so I can use the extension theorem. Again, you just cut and paste the slides. Think of it. You're just reproducing the same argument over and over again. The details change in terms of the algebra, but notice the calculus is exactly the same. That's what I like about this. I try to represent it in a generic way, right? The rule details are here, but once I turn it into the function f, the function g, the limits are the same due to the extension theorem. I can evaluate the limit of g of x as x goes to 0 because g is continuous. And I just figure out what the value is. And notice that they're the same steps over and over and over again. You don't need to reinvent the wheel, right? No matter what you're doing these steps, whether you acknowledge it or not, or understand it or not. I mean, I had that example in in the lecture about shortcutting. And again, it's fine if you understand it, but if you're just doing it and don't understand it, that's not good. Right? So again, you should know if you have these same steps work, the same process works if you're doing a two-sided limit. Of course, the two-sided is the one-sided. If you're just doing it from the left or the limit from the right, it would be exactly the same steps. You don't need to reinvent the wheel. So here's one for the left side of the same problem. And I'll just be quick because it's the same. Right? It's going to be exactly the same slides. I should have just probably shortened it. But notice everything proceeds exactly the same. The only distinction is since I'm doing a left-sided limit, I call it G minus. That's just mine. You don't have to, actually. You don't have to. But since I'm doing a left-sided limit, notice I just copied the same slides and turned everything to G minus. Oh, I even messed it up here. This should be a G minus, right? A G minus. So I got lazy or I missed this one. It should be G minus. But this would be the same. So, okay. So it should have been G minus. All right. Well, that's fine. I mean, again, the only typo here is this should be G minus. Yeah, I got lazy. I mean, I missed it. I don't know, lazy. I just missed it. So G minus. Just put a G minus there because that's what I was calling it. I mean, that's my notation. When I do 0 to the left, I like to do, G minus is the function. Now, here's a first different case, right? We talked about this in our lecture. If you want to pause and give it a try, I think that's a great idea and come back. If not, we'll go. But I prefer you try it yourself. You can look in the notes and just carry on. It's the same thing. Okay, if we're going to continue, then let's look at it. I'm going to look to define the function. Again, there is a domain and a range, right? It sets x and y. And the function, it's one function with two distinct rules, right? That's what's going on here. It is one function, and there are just two rules. One rule applies to numbers that are less than 1. Another rule applies when x is greater than or equal to 1. So is the limit point an element of the domain? Yeah. 1 is in the domain. That's correct. Is the function point continuous at a equals 1? We don't know. I mean, the issue is we don't know. If there's a different rule to the left and to the right, it may turn out to be point continuous, but at this point in the problem, I don't know. So I can't use the point continuity definition, right? I just don't know. I can't say. So the only tool we have is the extension theorem. So we're going to have to evaluate the limit to the left and the limit to the right separately. So here's my function. So what would be the left extension? What would be the right extension? Okay, so the left extension, I'm just going to take the rule that applies when x is less than 1, right? And again, notice I extend it to the whole real line, right? Whereas for the function, it only applies when x is less than 1. So it extends this rule. Okay, and on the right, what do? I take the rule from the right, and notice I'm going to extend that rule to all real numbers, and not just say x greater than or equal to 1, but all real numbers. So I'm extending that rule. And then we just proceed, right? On the left, it's going to follow exactly the same. On the right, it's going to follow exactly the same. And I just summed it all up. The left is on the left side of the screen, the right is on the right side of the screen. There's my left extension. I check that the rules match, that the left extension is a polynomial, it's a point continuous. I apply the extension theorem. On the right, I define my right extension. The rules are the same for all x greater than 1. Notice again, I don't have to say greater than equal to 1, just greater than 1, right? Because a limit doesn't need you to be defined. The rules don't have to be defined at 1. You're just talking about to the left and to the right. I write extension as a polynomial, so it's point continuous, and using the extension theorem, therefore, I know they have exactly the same limits. I can just plug in because I know the extensions left and right are continuous. And I just evaluate them by plugging in, and it turns out they do indeed have the same limit. And so they have the same limits, right? And if the limit from the left equals the limit from the right, oh, here's a typo too, right? It should be 1 minus and 1 plus. Boy, you notice a lot of these things now. 1 minus and 1 plus follows by the definition that the limit equals 2, right? The limit from the left and the limit from the right. So again, this is just really shorthand notation for this if I didn't have a typo there. I should have a plus in here. Okay, so again, that's more on the complicated side, but hopefully you're okay with that. Okay, so is the function point continuous at a equals 0? Well, how do you decide that? You just go through, again, you can do the definition, but I gave you 3 steps that you need to verify, right? You have to say that the function is defined at the point x equals a, in our case a equals 1. You have to check if this limit from the left equals the limit from the right, and you have to check to see if the limit equals the value of the function there. So we just check these, it's a checklist. Go ahead and pause and try them and just see. What I want you to understand is there's a method to everything. You don't do it one way for one problem and a different way for another problem. You want to do everything the same way, right? The same process. Okay, so there's my function again. Is the limit point a equal 1 an element of the domain? Yeah. Yeah, it does. F of 1 is, you can get a number out of that. It's 2. Right? It's 2. Second thing is, does the limit exist? Yes, we did this in the previous example. We looked at the limit from the left and we looked at the limit from the right. They were the same. And that's what this means. Limit as x goes to 1 plus or minus equals 2. So the limit exists. And then does the limit equal the value of the function? You just check. So check, and you're done. So again, by definition, not my opinion, your opinion, whoever's opinion, by the definition, f is point continuous at a equals 1, right? So, I mean, that's good. Now, here's another problem, and again, we're getting a little more sophisticated, right? Here's another problem. So what's the unique feature here, right? It's this absolute value here. And again, this comes out naturally. Look, when you look at this preliminary step 0, I have to simplify this. Remember we talked about this before in the first lecture. Absolute value is a function in itself, right? It's a piecewise function. I need to get rid of that. I mean, I just need to get rid of that. I mean, there's no sense keep carrying this around. So what we're going to do first in our step 0 is the algebra. Let's get rid of this. This is the definition. Now, again, I could have an x in here because it is a function. But I just don't want it to get it too confused, right? So notice a is x minus 3. Right? Everywhere I have an a, I just cut and paste and drop in an x minus 3. And I'm just going to clean it up. It's not really helpful. Like I said, this is better to write it as x less than 3. Right? It's just not very helpful to write it in this way. I just want a quick check on the x values. Right? And I distributed the minus sign through. So it should be 3 minus x. So again, let's go back and see what we're doing. This is our function rule right here. And this is the definition for x minus 3, the absolute value. Let's just plug this down in here. Right? Let's just plug this down in here. So we have that, and now 2x is how we're going to deal with that. Well, it's 2x everywhere, right? This is another way of writing 2x. It would be 2x as long as x is less than 3. See, I'm pairing up the rules here, and it's 2x when x is greater than 3. Right? So it's 2x in this part of the rule, and it's 2x on that part of the rule. And then I'll just do the algebra and clean it up. So that's really what our function is. So f of x is really just this function. So why did they write it like this? They gave us, I don't know, that's what they did. So this is really what we need. And this is all preliminary. This is all algebraic. This is pre-calc kind of stuff. But if you're uncomfortable with it, work through it. Try it. Don't be intimidated by it. So we have all this here. And this is what we're working on. So notice this is just piecewise. It doesn't look it maybe, but this is just piecewise built around 3. And so how are we going to proceed? Exactly the same as the last example. Exactly the same manner as the last example. You're going to have to look at left and right. So let's look at it. The limit point a equals 3 is an element of the domain. Check. But I can't just apply the point continuity, point continuous at a equals 1 definition because I don't know if it's continuous. It may turn out to be continuous, but until I check, I don't know. Right? That's the difference here. Like a polynomial. I know if it's a polynomial, it's point continuous. But this, I don't know. So we just do left and right hand limits, extensions, right? Left and right hand extensions. So on the left, here's the original function. I'm going to take the rule that applies on the left. And on the right, I'm going to take the rule that applies on the right. And at this point, we just go. Notice the function rule equals the extension in both cases. Both extensions are polynomials and so continuous. And so I can just plug in, right? I do the left side, the right side, use the extension theorem, use point continuity, and evaluate the particular rules. And I have the limit from the left is 6, and I have the limit from the right is 6. Now, I'm not saying this is an easy problem, but notice what makes this problem more challenging is the fact that you do all that algebra in the beginning. Everything else should be more or less standard. Since the limit from the left equals from the limit from the right, I don't have a typo this time, that's good. Then I can say the limit exists, right? Again, the box is just shorthand for this line. So that's it. That's pretty good. This covers all the types of examples you could possibly see from me. You should try some of the homework. Make sure you're comfortable with it. In the lab on Fridays, we're going to work on problems like this. So again, make sure you're comfortable with this. If you're not, you should talk to us, and you should be. This is not something that should cause you undue stress. If you're having trouble, it's probably a very specialized algebraic gimmick. Just look through the book or ask us about that. Okay, so good luck with that.